Okay, so hello everyone. So let me introduce myself first. My name is Wei Zhang. I'm a senior scientist at Genentech. Genentech is a biopharmaceutical company in USA. It's a part of the Roche family. Roche, our parent company, is in Switzerland. Today I'm going to talk about my research closely related to industrial pharmacy. Focusing on the impact of polymer type, ASD loading, and the polymer-drug ratio on the ASD tablet disintegration and the drug release. So here is a brief introduction of the amorphous solid dispersion formulation, or the ASD formulation. An amorphous form of a drug can have a higher Gibbs free energy. So this is the intrinsic driving force that an amorphous solid can have a higher solubility. However, due to this higher Gibbs free energy, amorphous drug can also have the inherent tendency to crystallize. Therefore, to prevent crystallization, the industrial scientists will add polymers with the amorphous drug to form amorphous solid dispersion. This can stabilize the amorphous drug at the amorphous state, both in solid state and in dissolution process. So for us, when we develop an amorphous solid dispersion formulation, we have a decision tree here. So first of all, because of the crystallization risk, we need to carefully evaluate whether it's necessary to develop amorphous solid dispersion formulation. Usually, the primary driving force is that we want to increase solubility of a pharmaceutical molecule. Another driving force is sometimes crystalline form of some drugs cannot be developed. Then in this case, we need to consider amorphous form. If the decision of ASD formulation development is made, the next step will be screen the composition of the ASD formulation, including polymer and surfactant. So when we do the composition screening, we will consider physical stability of the ASD prototypes and the supersaturation maintenance of the ASD in dissolution process. We will also consider chemical stability and ASD manufacturing method. After the composition of the ASD is fixed, we will develop the ASD and focusing on downstream processing. This includes how we manufacture the ASD, what is the powder flow property of the ASD material, and what is the compaction property of the ASD material. At last, what is the ASD tablet, the final dosage form, disintegration and dissolution performance. So today I'm going to present two topics. One thing is about the solubility advantage calculation. The other thing is the ASD tablet disintegration. So for the amorphous solubility advantage calculation part, in the past several years, I did some research validating a theoretical model for calculating the amorphous solid solubility advantage for drug molecules. So here is the model published in the literature. If you have a amorphous drug and a crystal drug, their solubility ratio can be calculated by thermodynamic equations using the Gibbs energy difference between the two forms, and also one term called the water absorption term. This is because the amorphous solid can absorb water, and the water absorption can reduce the drug solute activity, and therefore this number is always less than 1. So the water absorption will reduce the solubility advantage of amorphous material. In a buffer system, the amorphous solubility advantage can be calculated from this equation. And for the first term, this Gibbs free energy term, R is a gas constant, T is temperature, and we only need to find the Gibbs free energy difference. A simple equation to calculate the Gibbs free energy difference involves melting enthalpy and heat capacity difference between the crystal and the amorphous form, and the melting temperature and the temperature of interest, usually 25 degrees or 37 degrees. So all these parameters can be measured by a conventional tool called a DSC, differential scanning calorimetry. And this water absorption term can be calculated based on data from DVS, dynamic vapor absorption. So for calculating the Gibbs free energy term, delta G. So here is one example of a model compound, ritonavir. So we can measure the glass transition temperature, Tg, of the molecule. We can also measure the melting temperature and the melting enthalpy of the same molecule. And then in the same time, we can use modulated DAC to measure the reversing heat capacity between a crystal and a liquid and a amorphous form. So when we obtain the glass transition temperature, melting enthalpy, and the heat capacity difference, we can calculate the delta G using the equation on the one page before. Similarly, for the water sorption term here, we can measure the amorphous solid water sorption kinetics. This is the weight change based on water sorption as a function of RH. And then by rearranging the data here using an equation called Gibbs-Duhamel equation, we can calculate what is the solute chemical potential at a different water activity. Then we can extrapolate a little bit to 100% water activity. Then we can get the water sorption term for the molecule. This is again for ritonavir case. So you can see for ritonavir, the water sorption can reduce the chemical potential of the molecule from 1 to about 0.3. So using the method, we studied 10 compounds, including public available model compounds. Ritonavir is here. So we studied these model compounds, and we also studied a full confidential compound from our company, including one molecule, Genentech B. So the structure is released. So this is the structure of the molecule. And also we studied another 3 compounds, Genentech A, C. C had 2 solid forms, 1 and 2, and Genentech D. For this, in total, we have 10 molecules and 11 solid forms. And so to verify if the calculation is accurate, we did a solubility measurement experimentally. So again, I'm showing ritonavir as one example. We measure the solubility of the crystal form and amorphous form by a technique called microdissolution. So this microdissolution can monitor the concentration in real time. Therefore, by this method, we can know if there's any precipitation from the supersaturated solution. For ritonavir, we made the amorphous solid by different methods, including lyophilization, spray drying, precipitation, and melt quenching. So here you can see 9 of the amorphous solid desupersaturate in the measurement. And we can get the amorphous solubility when the concentration reaches the plateau. Here is the crystal solubility as a comparison. Using the same method, we measured all the experimental solubility for the different compounds. And here is the comparison for the 10 compounds. The y-axis here is a measured solubility advantage, amorphous solubility over crystalline solubility. The x-axis is the calculated amorphous solubility over crystalline solubility ratio by the theoretical equation. We can see that most of the compounds, they agree with the theoretical calculation pretty well. The outlier here is still within 2 folds. So if we view the data in a different way, so this is the calculated amorphous solubility advantage over the measured real amorphous solubility advantage. So this is the different compound. We can see all of the compounds are within a factor of 2 accuracy. Some are very close to factor 1, meaning they are pretty accurate. This is outlier. Tafenidine is also this data point. This one is the deviating the most. It's within 2 folds still. So this is the part 1 of my research. We applied this theoretical equation to the development of amorphous drug formulation in our company, and we started with this to verify what is the amorphous solubility advantage, and then we did a composition screening, and at the end we developed an AST formulation for the molecule GNEB. So here is the second part. How did we evaluate the AST tablet disintegration for the GNEB molecule? Again, here is the GNEB structure. In this study, we evaluated the different polymers to form the amorphous solid dispersion, including PV-PVA, HPMCS, HPMC. PV-PVA and HPMC are water-soluble polymers. In water, they have solubility greater than 20% in weight, or 200 mg per ml. HPMCS is generally not water-soluble. When we measure the visual solubility in water, is less than 0.1 mg per ml. And because PV-PVA and HPMC are water-soluble, so they are polymers, so they can increase the viscosity of the medium. Here, the viscosity in log scale versus the concentration of the polymer in water or in our dissolution medium. So you can see both PV-PVA and HPMC can increase the viscosity of the solution with the concentration. And HPMC increase the viscosity more significantly than PV-PVA. For HPMCS, we don't expect there's any effect on increasing the viscosity because this polymer doesn't have much solubility in the aqueous medium. To investigate the effect of ASD loading on the tablet disintegration, we made our ASD tablets using Genentech ASD. So this ASD contains different polymers for different prototypes. For example, we have a PV-PVA ASD, HPMC ASD, and HPMCS ASD. Within the ASD, the drug to the polymer ratio is always 60 to 40, meaning it's a 60% drug loading ASD. With different ASD percentage in the tablet, 20 to 80, we adjusted the filler of the tablet. The filler we use is MCC, microcrystalline cellulose, or avisol pH102, and the lactose. We use the cross-carbonyl sodium as a disintegrant and the manganese stearate as the lubricant. For the tablets, we are targeting 2 megapascal tensile strength or 25 kP hardness. The solid fraction of the tablet is about 85%, or the porosity is about 15%. So after we made this tablet, we tested our tablet disintegration time in the dissolution testing. So here we can see as the ASD loading in tablet increases from 20% to the 80%, the disintegration time of our ASD tablets in general increases. And especially for the HPMC, the blue bar, it increased more significantly than the other two polymers. HPMCS increased less significantly compared to the two hydrophilic polymers. So our conclusion is that with the increase of ASD loading, the tablet disintegration increased, and HPMC had a most significant effect. In the meantime, when we test the disintegration time, we also evaluate the dissolution of the ASD tablets. So this is the drug released versus time at 20% ASD loading, 40% ASD loading, and 60% ASD loading, and this is 80% ASD loading. So at a lower ASD loading, we can see for different polymers, they all achieve the full release, and the profile pretty much similar. When the ASD loading increases, the HPMC ASD tablet began to slow down compared to the other two polymers because of the long disintegration time. And with further increase of drug ASD loading, the PV-PVA ASD also began to slow down because of the increase of disintegration time. At 80% ASD loading, HPMCS based on ASD tablet can still release some drug, but the other two polymers can almost release less than 20% drug. So this dissolution testing result is consistent with the disintegration testing result. After studying the ASD loading effect, we also studied the drug polymer ratio effect. For this study, again, we use the Genentech ASD. The ASD is different prototype, including PV-PVA, HPMC, HPMCS. The ASD loading in the tablet was fixed at 40%, but the polymer to drug ratio in the ASD changed from 20 to 80. So 20 is the drug and 80 is the polymer. Then we increased the polymer ratio to 60, 40, and 20%, 80%. Again, we use the same filler, same disintegrant, and the same lubricant. Here's the disintegration time for the different AST tablets. We have HPMCS, PVPVA, HPMC, and the polymer-to-drug ratio increased from 20 to 80 to a higher polymer-drug ratio, 80 to 20. At a lower polymer-drug ratio, they all have a fast disintegration, but with the increase of the polymer-to-drug ratio, the PVPVA and HPMC-based AST tablet had a prolonged disintegration time, especially again, HPMC AST tablet showed the most significant increase of the disintegration time. For HPMCS-based AST tablet, the disintegration time actually didn't increase too much. It maintained a very fast disintegration time, although the polymer-to-drug ratio increased significantly. So we get the conclusion that with the increase of polymer-to-drug ratio, disintegration time increased for PVPVA and HPMC-based AST tablet, but maintained rapid for the HPMCS-based HPMCS AST tablet. And the effect of HPMC is more significant than PVPVA. So this is probably related to the viscosity increase due to the HPMC solution. So from the dissolution testing, we observed the consistent results. At a lower polymer-to-drug ratio, their dissolution profile are similar. With the increase of polymer-to-drug ratio, HPMC began to slow down first. And then with further increase of the polymer-to-drug ratio, PVPVA-based tablet also showed the slowdown of the dissolution. When polymer-to-drug ratio reached to 80 to 20%, PVPVA and HPMC-based AST tablet showed less than 100% drug release, but the HPMCS tablet can still maintain full release of the drug. So to understand what's happening, we made the tablets at 100% PVPVA, 100% HPMC, and PVPVA to drug 80 to 20% ratio, or HPMC to drug 80 to 20% ratio. We exposed the tablets to water for 10 minutes, and we found that due to the high viscosity of the polymer in water, the surface of the tablet became a gel, and this high viscous gel can prevent water penetrate into the tablet. So this gel layer and the inside of the tablet still maintain a dry core material. So this prevention of the water penetration can prevent the disintegration of the tablets. To summarize my presentation today, so in my research, I was able to validate a Morpho solubility advantage calculation method by experimental measurement, and we also studied the polymer type, AST loading, and AST composition on the tablet disintegration. We concluded that the hydrophilic polymers can form gels upon exposure to water. This can lead to water penetration difficulty and prolonged AST disintegration time. It's more severe if we have a higher AST loading or higher polymer-drug ratio. It's more severe if our polymer solution has a higher viscosity. If we want to develop a high AST loading tablet, hydrophobic polymer like HPMCS is recommended, especially when the higher polymer-drug ratio is needed to maintain the Morpho-drug stability. Yeah, I think that's all for my presentation today. Any questions?